and Chloe as well. She's gonna do so. We'll start giving a quick overview of what we do, a little bit about the architecture, and then we'll jump into a demo that she will run. So Dozer is we founded this back in September 2022. We are in the data space. We'll go into the details. We are VC funded, and we are fully open source under Apache 2 license. And you can take a look at our repo there, and you can play with it, and you can start if you like. Okay, let's jump into so I don't know how many here are working on data specifically, like data engineering, but one of the biggest problems that you have when you need to take your data from your operational system or your analytical system, your data warehouse, and you need to expose it to customer-facing application, you have to build a lot of stuff. It seems a very trivial task, actually, because you say, I already have all the data there, I just need to expose it, but it's not that trivial. And you most of the time you have a bunch of data sitting in different places, like could be OLTP databases, could be on your Amazon S3, could be on your Snowflake or Delta Lake, whatever. You might have a bunch of batch processing to do, a bunch of real-time processing to do. So what you usually do, you start bringing up a Kafka for the real-time streaming, Flink or Spark for real-time processing. You have to orchestrate some batch workloads, so you will start bringing up Spark, for example, Airflow. Then once you did all the processing, it's time to serve the data. In order to serve the data, you have to store it in the appropriate store. So what you do, you bring up something like Elasticsearch, depending on what kind of pattern the application is interacting with. You bring up an Elasticsearch, you bring up a Redis, plus some custom code to stitch everything together, and finally you can consume the data in your application. Not to mention the operationalization of this. So one thing is deploying and building, then you have to maintain it, you have to run it. What happens when there are schema changes, new version of APIs, etc., etc. So I've gone through this problem multiple times, and I said, okay, there should be an easier way, especially why do I need to bring up all this infrastructure fully distributed when maybe the volume of data doesn't really justify it, actually. So we came up with this idea that we call Dozer, actually, which is an end-to-end solution allowing you to connect sources all the way to consumers' application. So it's fundamentally an end-to-end tool that embeds data capturing in real time from multiple sources, transformation using SQL or we're working on WebAssembly, caching. So once the data is transformed, is stored in a low latency caching layer, the generation of the API, and the security on top of the API. So with a simple configuration, you can say, I want to get a bunch of data from my sources. I want to transform it. I want to cache it. This is what indexes I want, and the API are auto-generated. As you can see here, everything is in real time. So even if a source is basically batch, we treat it as a real time. So we detect the differences. And the transformation engine is basically a streaming SQL engine that processes the data while the data is in transit. This is a simple configuration, then you will see a live demo, but it's basically 3 blocks to define everything. You define your connection. In this case, I have a Postgres connection and I have an Ethereum connection. I have a SQL that does some aggregation, does some joins actually, and then I say, okay, you can see in my SQL, I'm mentioning here into address stats, and address stats is basically my endpoint. With this simple configuration, I can basically deploy a backend for a data API application. once you deploy it and you have the caching layer, the API that you get exposed to interact with your application are fundamentally gRPC and REST APIs, and all the contracts are basically auto-generated. So you get Open API contract and protobuf contract that is auto-generated, and on the when you query the data from the caching layer, you have some basic operation like standard operation like filtering, sorting, and pagination, because the whole idea is that you do this simple operation. We want to keep the latency constant, actually. You do this simple operation when you query the data, and the complex operation like joining, aggregation, you do it upfront. So basically you pre-materialize your query. This is, I'm gonna go a little bit through into the details, not too much, to explain a bit about the architecture of Dozer. So it's split up in, I start saying it's all implemented in Rust, actually. And then we have client and bindings in Python, which we're gonna show later today. We have 4 major components, if you see. We have connectors, pipeline execution, cache, and API. Connectors, it's a pluggable connectors model that you can easily create additional connector. And what the core of the core of the engine is basically the pipeline execution and the caching. The pipeline execution is it's fundamentally an implementation of a streaming SQL engine. So we take the SQL, we transform it into a DAG, the direct acyclic graph, and each node basically maintains a state and process the incoming data. After your materialized view is calculated, we have our caching layer or our cache writer where data is stored. And on top of the cache writer, you see we have our cache reader with the API and authorization on top of it. So basically, this is how Dozer is. It can run as a single binary, or it can be split up in multiple containers for a more complex deployment. This is a little bit about the connectors. It's a very simple interface, the connector. And this is what we currently support. We support Postgres, Snowflake, Object Store, Delta Lake, Ethereum. We support gRPC API, so you can ingest data from your own code. We're going to have a sample later. And then we have a bunch of other connector coming up soon. As I mentioned before, even when we try to leverage always the streaming aspect, even if the source is not strictly streaming. Take, for example, in Postgres, we always use CDC, Delta Lake and Snowflake, we use table streams, and even files, we basically auto-detect the differences and propagate the difference to the engine to have always an incremental approach. Next one. This is a bit about what I was saying before about the pipeline execution. That SQL is translated into a DAG. We have 3 different kinds of nodes. We have source nodes that pumps data in. We have processor nodes that basically are implementing each and every operation. So imagine you have aggregation, you have joins, so each node represents a different operation, and each node maintains a state. Fundamentally, this node, they handle 3 types of messages: insert, deletes, and updates. So by replaying all these messages, you can basically create a state, and that state is then maintaining the pipeline and propagated down to the caching layer. This is, okay, you can go back. Yeah. This is a sample DAG of taking this query. You have a select, you have into, you have from, and you have a couple of joins. Here you have your tables. Then you have a product processor, which basically does the product. And then you have a projection processor that is extract the field that you want, and then it goes into the sink, the cache sink. About the processor itself, it's fundamentally a processor exposes an input and an output port, a multiple output port, fundamentally, a multiple input and multiple output ports. And the role of the processor is basically translating this input into an input message into an output message. So fundamentally, let's say you have a join processor, you have two inputs, you get two insert messages, and you perform the join. Obviously, a state must be maintained, and a new insert operation is emitted. So the advantage is that whenever something changes on the source, on one of the source, the join is automatically recomputed. So the advantage is that your cache, your sync, is always in sync with the source whenever something changes. That's the advantage. The cache writer, it's go very quickly here. It's fundamentally, it's based, we did a lot of tests in the beginning to evaluate what was the best. We didn't want to rely on a fully distributed database or key value store to handle our cache because it complicates things a lot. We wanted to keep it very simple. So we evaluated two options. One was RocksDB based, another is LMDB. We chose LMDB because what we care mostly is read performance rather than write performance. RocksDB is very efficient when you do a lot of writes, being merge tree based. LMDB is basically a memory mapped B tree, and it's a little bit slower in the writes compared to a RocksDB, but it's way faster in reads. That's what we care. Yeah, another thing that we handle automatically is a non-trivial thing to handle is the blue-green deployment of the cache. Imagine that you do some changes of your SQL, your transformation. So basically, you are changing the generated schema of your data. Now, your new schema might not be compatible with the old schema, but you still have some clients that are using your existing API. So what we do, we detect the schema change. If there is no schema change, it goes, it's flawless. If there is a schema change, we bump the version of the API and we start backfilling the data so that now you have two versions of caches, two versions of API running parallelly with two different schema, and you can decide when you want to switch from the old version when you have migrated your mobile app, your web app to the new version. That's another thing that we. On top of our cache, we basically support indexes, obviously primary index, secondary inverted index, and full text index. That's what we support. So basically, you can do query by any field or full text if you want. The cache reader is basically what sits on top of our caching layer and exposes the data through to the API. That's what I was mentioning. The query that you have available here are get, count, query with some filtering, and we have a minimal implementation of a query planner because the operations that we do in the query are pretty straightforward. Yeah, that's about it about this. API, we expose, as I said, gRPC and REST API. For REST API, based on your SQL that you define, we generate an open API definition contract, and for gRPC, we generate a protobuf definition as well as expose the gRPC reflection. So you can to use it from tools like Postman. As I mentioned, we take care of versioning, automatic versioning of the API, and we have a level or authorization on top of it using JWT token. So you do your authentication, we use a embed the role in the JWT token so that you only get visibility on a slice of data that is assigned. So fundamentally, the JWT is assigned, embeds a filter that is automatically applied to the data itself. Another interesting thing that I haven't covered, and we're going to show the example, is the concept of change data function. So imagine that in addition to store data in cache, you want to trigger functions when something changes in the data. This is one example. I have a query like the one before, and then I have a condition. This is a flight departure. I say I have a condition where actual departure is different than scheduled departure. So when somebody changes the actual departure, for example, the plane is late, in the source system, that triggers the CDC, which goes into Dozer and gets catched by SQL query. Now, when this is detected, it triggers an execution of a Lambda function that is implemented in Python or in JavaScript. So in that context of a Lambda function, you can pretty much do anything you want. You can trigger a message, you can write back to the source system as well. So that is our way of not just being a read-only system, but allow you to interact with the system itself by writing back or trigger messages and notifications. We have a bunch of client libraries. We have two types of library. For consumption, so that means for consuming the API, we have Python, JavaScript, and React integration. So it's pretty straightforward to, once you use Dozer to implement the pipeline to use it. And then we have an ingestion, Python library that allows you to pump data into Dozer programmatically. And this supports plain Python, or it interacts with data frame pollers, actually. I think that's it for the slide. She's gonna run a demo of Dozer, right. So you can,
yeah, nothing special. I'm just gonna be going through a sample data app today. So the sample data app that we're building today is gonna be based on a very simple IoT device, which captures a temperature of the room every 1 second. And if the temperature goes up a little too high, then we uses the change data function that Matteo just mentioned to capture the changes, and we basically expose an alert using Dozer. So key point here would be the demonstration of Python client library as a data ingester. Like Matteo covered, it's just going to be pumping data into Dozer. Dozer is going to consume it, and then we're going to be serving that as a series of API. So let's get started. We can do brew, and in other architecture, we do have stated in our website how to download it. So we can start by installing. Yep, this will do the job. So our latest version is 0.1.22. Yes, we're getting the right version. And once that's done, you can verify on your successful installation by running Dozer help command. By right, this will show all the available commands that you can run on our latest version. So to me, Dozer init, which initialize an app using a template, sounds perfect to start with. So it will require some of your inputs, such as app name, blah, 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 but I'll be taking default values for now. And as Matteo covered earlier, we do support a lot of different types of connectors. Here, what we require is basically in terms of you are using specific connectors that you are having in your mind, we are giving you a guidance how to plug in the right information in the right format. So I'll just taking the default, and let's see how this command does. So it will create a config file in your workspace named after dozer-config.yaml, and it will populate it, the file with this template. But template, as I said, is just for your guidance to provide the right information in the right format so that Dozer can understand. But today, what we're going to be covering is the bare minimum to start with Dozer. So all we got to do to key in is just 3 things. Starting with connections, and when it's sources, and lastly, we need endpoints. Sorry. Yeah. So connections are simply the information that Dozer needs to connect your database. So as we covered, this demo is going to be ingesting data from Python client library, which is going to be on top of gRPC API. So we're just going to be configuring a gRPC connection. And gRPC connection, to have a valid information, we do need a schema placeholder. And I created this simple JSON that that we require is a table named after events, which has a schema of 3 different fields: string type, device ID, float type, temperature, and string type of timestamp. So we're just going to be letting them know that we do have this file in this path. And also we do need to specify on which port that we're going to be connecting towards each other, ingester towards Dozer. And so we're just going to be letting them know as 7001. And I'll be just naming this connection as temperature so that we can access to this connection as a reference in other sections. So that's done for your connection. And moving on to sources. Sources are basically what kind of table that you want to go access, get your data. So here, as we already specify in a schema, we do need a table called events. So it's going to be event. And we are going to be having a connection over the one that we just specified above. And you can also specify on the list of columns that you want to fetch data from, like certain columns like 1, 2, 3, and not the others. But by default, you can fetch all the others by just leaving it as blank. And I'll just name this source as events, following the simplicity. And lastly, yes, we're ended up in the endpoints. So endpoints are basically what Dozer should generate after all of this. So we're generating an API, and that API is going to be exposing all the data in events. It's very simple. So we're taking data from events table. It needs to match here. And the path that we are going to be using for this endpoint, I'll just follow the table name. And in case of you want to specify on your indexes, like Matteo covered, like primary index, secondary index, you can do it, but I'll just leave it as blank. Oh, sorry. Yep. And also I'll give a name after its path. And this is basically the bare minimum that you need to run the Dozer. You can just go back to your terminal, run Dozer, it should work. But we need another revamp here because we want the notification to be given to us when there is a temperature going above a certain level. So to do that, we are gonna do a real-time SQL data transformation, and that's gonna be connecting with our change data function that we're gonna be using in the Python client library. So all you gotta do is just add a SQL section, and here I'll be selecting, for example, my ID column, my temperature column from events table, where temperature is greater or equal to 23 degrees, for example. That's pretty much it. And we're going to be exporting this results as a into clause, for example, alerts. Then we're ready to go. So this alerts is going to be working exactly the same way that our events table are working. So I'm just creating another endpoints, which does exactly the same, but just only exporting the data from our data transformation. So all you got to do, change the table name into alerts, change your path, change your name. And we're ready for running Dozer. So now what you got to do is just run Dozer. If you have a custom config name, you can use -C, but I'll just run it. So in a few seconds, it just shows you what version that you're running on. And as Matteo covered, by default, Dozer automatically provides 2 different types of API per endpoint, REST and gRPC, running on the default ports. And as we specify on the config, we do have 2 endpoints being exposed as a result. And we can also see that we have been successfully initialized our input schema that as we specify in the JSON file. And actually the events and alerts are there, but there's no streaming of any consumption of data coming in yet. And we can see that our REST API and gRPC server is up. So now what we gotta do is let's pump data in. So to pump data in, let me go to something familiar to you guys. It's a main.py that we're gonna be using as a data ingester. This data ingester is importing our Python wrapper called PyDozer. If you want to use this in your project, all you got to do is just pip install PyDozer. It has two different submodules, ingest and API. API is the one that consuming the data. Ingest is basically for our data ingester. So we're going to be concentrating on the ingest module today. And to initialize your ingest client, all you got to provide is what kind of port, what kind of URL that you're going to be talking to our Dozer. As you specify in the config, we're just going to be using exactly the same. And our main run function, what it does is we do have a data on our CSV file. It's coming from an IoT device. And we're reading data row by row, and we access to a column that we want to get data from. Like, for example, in this case, it's a device ID and temperature. We call this function call sendMessage. Within sendMessage, we are initializing ingest requests, which needs some details around what kind of schema, what kind of output schema that we're targeting, and how each records are going to be structured. So in this case, we're going to be having 3 different fields, 3 different values: string for device ID, float for temperature, and string for timestamp. So once your request is ready, we're utilizing the pre-initialized client to send the request by calling this ingest raw function. This ingest raw function is to just pump out the data in common format. But in case if you want to use it in a streaming manner, you can also use ingest raw stream. And as Matteo covered, if you want to use a polar data frame, you can also use a DF, and you can also push it in an arrow format. So yeah, we're ready to go. Let's run. So once we started running, it is pumping data, and Dozer is reflexing with the data inflow. And as you can see, our events endpoint is consuming data as we are pumping, because we're basically exposing all the data as an API. But alerts, in other case, is only consuming data when there is a condition met that we have set in the SQL. So we have said that the temperature has to be larger or equal to 23 degrees, and there's only one data point that is coming in, which is actually under that condition. So this is basically our data flowing in. I want to check the data in API format. So you can use whatever tool that you want to use, but today I'm going to be using Postman. So for gRPC, we're using server reflection. We do have some common gRPC health and authentication services by default. And on top of it, we can also see an endpoint that we defined in our configuration. So let's start with events. So events supposed to have all the records that is pumping in from our Python library. Seems okay. And you can also check on how many records are coming in. It's keep increasing because it's still running. And for alerts, there should be only one data, and it is reflected in our API as well. So same data can be represented in a REST format. For REST, we're listening on 8080. And if you give a GET request to the path that you defined, then you will basically get the same thing, but in a REST format. And what we also can do is giving a post request to do a post filtering, or so-called like transforming your data as you need. So there's 3 different parts that we support. One is limit for your pagination. So it basically limits the output size of the records. And the filtering you can do on top of the value that you're getting. And there's order by. So in this case, what we are doing is by getting the whole data, we only want those record which is greater than 22.3 degrees. And I want it to be in ascending order, and I just need 2 records. Then it's just going to give us that. And last but not least, we also do provide a open API config. So on top of any endpoint that you specify on your config, just /OAPI and give a post request, then you will get this configuration handy right away. So yeah, that's how the data should be looking, but we're still missing one bit. We need an alarm. Yes, we need an alarm. We do have alerts data flowing in, but we don't know how to alert this back to us or back to anybody. So we are creating another file. We are utilizing that Twilio client to give us SMS message when there is a temperature going above 23 degrees. So what we're gonna do is, let me stop it for a while. And let me go through. So in this async main function that we're having in the reader, the file, it uses a PyDozer_log. So this is another Python library that we're importing here. It basically does a change data function detection by reading all the logs that is coming from certain endpoint that you specify. So in this case, what we're doing is we are initializing a log reader for an alerts endpoint. So if there is any data coming in as an operation, we basically gonna send a message. So what does that mean? So if data flowing into an alerts endpoint, that means it already met the condition that we set in the SQL data transformation. So basically means there is a data which is going above 23 degrees and the room is getting hotter. So let's run it. So I'm gonna be running Dozer, and I'm gonna be running reader. Reader's up, and there's no data flowing in yet because we didn't pump it. And let's go. So Dozer is consuming, reader's consuming. Let's give it a moment until alerts get any data. All right, it prints out in our log saying that the room is getting hotter. And my text message is here saying that the temperature of the room is getting hot. So it can be utilized in any form, but I'm just showing it as an SMS message today. And just for a better visualization, we also do have a JavaScript and React client that has a client library like Python. And this simple website is built on top of it. It just takes the coordinates from Dozer and just represent it as a real-time graph. So basically, this is all we prepare for today. All the samples, related files, resources are actually available in our GitHub. So you guys can check it out, and even for the website. And also we are supporting a lot of connectors, yes, but we're keep expanding and we are getting a lot of feature requests. You can contribute if you want, using your own custom connectors. We're live on Discord channel as well. So feel free to connect with us and start us on GitHub. I think that would be it. Thank you.